Okay, so the next talk is by Alexander Liu on trace types and denotational semantics for sound programmable inference in probabilistic languages.
Okay. Thank you. So thanks, everyone. My name is Alex Lev, and I'm a PhD student with Vikash Mansinka in the Probabilistic Computing Project at MIT. And today I'm going to be sharing some work that some colleagues of mine and I have been doing on sort of how to do sound programmable inference. So it's going to be very related to the last talk. I think they'll go nicely together. So probabilistic programming systems, just to give a little bit of context, aim to make probabilistic modeling and inference techniques easier to use. And the idea behind many probabilistic programming systems is basically that the user is going to write down a probabilistic model as code in a probabilistic modeling language. They're going to feed it to the probabilistic programming system. Maybe they're going to choose an inference algorithm from some menu of inference algorithms. They'll put in their data and their query, and out pop results. And the system is going to automate the application of the inference algorithm to the model and the data. And this is great as long as you trust that the probabilistic programming system doesn't have bugs. And thankfully, there's been a lot of work in recent years, a lot of it appearing at this conference, that is sort of laying the semantic foundations of these languages and validating their inference engines so that we know that we can trust them. But this picture hides some complexity. If you look at the documentation for these languages, you'll see the inference algorithms that they use have names like Metropolis, Hastings, and importance sampling. But these algorithms, or these names don't describe algorithms, they describe broad classes of algorithms. Okay? There isn't one Metropolis Hastings algorithm. There's a whole bunch of Metropolis Hastings algorithms. Each of these classes of algorithms is parameterized by the choice of some auxiliary distribution, which we call different things depending on what algorithm we're in. So a transition kernel or a proposal distribution or a variational family. So in the last talk, there was talk of like the user writes a model and the user writes a guide program. That guide program was a variational family. Every different guide program that you write is going to lead to a different variational inference algorithm. Right? And similarly, every proposal distribution that you write is going to lead to a different importance sampling algorithm. And the reason I say that you write instead of that you choose is because a relatively recent development in probabilistic programming languages, including Pyro and many others, is that the user inputs this third thing. In other words, the user is not only going to choose an algorithm like Metropolis Hastings or importance sampling, an algorithm class, they're also going to write a second probabilistic program which specifies this choice of distribution that parameterizes the algorithm. Okay? So as a user, you write your model. That specifies what problem you want to solve. And then you write some extra probabilistic code, which is also going to be analyzed by the probabilistic programming system, which is going to customize the behavior of the inference algorithm on your model. So this leads to a big increase in flexibility. But as you can imagine, the correctness of inference now doesn't just depend on the probabilistic programming system's implementation. It also depends on this code that the user wrote, this inference code that the user wrote. And we saw some examples of that in the previous talk, the sorts of ways that things could go wrong if the variational family that you provided didn't satisfy certain properties, right? And so some of those properties are sort of properties in variational inference, but all of these algorithms have different properties that you're going to want to ensure about the relationship between these two programs, your model and your proposal distribution or guide program or transition kernel. And so in this talk, I'm going to spend the first chunk just sort of giving an overview, an inference algorithms crash course, or maybe a how to make inference algorithms crash course. We're going to sort of do a whirlwind tour of these inference algorithms and what can go wrong in them. Then I'm going to be talking about our approach to solving this soundness problem. And so what we've done is we've developed a sort of graded monad for probabilistic programs, where the index in the monad, so the type of a probabilistic expression, is not just going to track sort of its return type, it's also going to track the space of its possible execution traces. Okay? And what that's going to do is it's going to allow us to reason a lot easier about some of these measure theoretic properties that we need to ensure, and ultimately to develop sound by construction versions of these programmable inference features. Okay? This is building on a lot of the semantic, we validate these features building on a lot of the semantic work that's been done in quasi-Borel spaces, so giving a way to interpret probabilistic programs as measures, and especially building on this paper from 2017 by Sivyer et al., who provided a way of reasoning about the correctness of inference algorithms. And in fact, our Haskell prototype of our sort of programmable inference system builds directly on top of their Haskell prototype of their system. So it all integrates with monad Bayes. OK, so let's move on to the inference algorithms. So the tutorial inference problem that we're going to be solving today is robust Bayesian polynomial regression. So we're given a data set like this of x, y points in the plane. It might have outliers, it might have some noise, but we want to explain this data set in terms of a noisy polynomial relationship. That means that we want to, given a data set like this, recover all these latent variables that explain it, which include a polynomial curve near which many of the points lie, as well as classifications of other points as outliers that don't lie near that curve. And a sort of noise level represented here in this faint gray color. I hope that it's visible on the screen there, which is sort of the standard deviation away from the curve with which these points are generated. Okay? How do we tackle this problem using probabilistic programming? Well, the first step is to write a generative model, which is a program that models the process by which the data came to be. Okay? So in this case, we're going to write a helper model first called generate curve, which is going to be responsible for sampling polynomials. And it's going to do that by sampling a random degree. So maybe we chose like degree 2, and then sampling random coefficients to fill in the sort of coefficient slots in that polynomial, and then packaging it all up in a lambda abstraction that implements the polynomial function determined by this degree and these coefficients. Okay? So this is a probabilistic program over polynomials. And we're going to use that probabilistic program over polynomials to write a probabilistic program over data sets of y points. We're going to assume that the x points are fixed. Okay? And first, we're going to generate a random polynomial. Then we're going to generate some additional parameters that are going to tell us sort of how noisy the data set is going to be. So what is the prevalence of outliers in this data set, and what is the noise level? And then for each x point, we're going to sample a y point, and in order to do that, we're going to decide, is it an outlier or an inlier? So for each x, we're going to decide, do we want to generate an inlier or an outlier? And then we're actually going to sample points either near the curve or from a broad distribution, a broad outlier distribution. Okay? So that's how we get our data set. We've modeled the process by which a data set could have come to be. Okay? And every time we run this program, we get out a trace, which is a dictionary mapping the names of random variables to the values they took on in that execution. Right? So we don't actually just think of it as a distribution over data sets. We think of it as a distribution over explanations of data sets, right? Over all of these latent variables. And the names here are coming from, I don't know, I didn't point this out, but every sample statement that we make in this language, we're giving it a name. Right? Okay. And we can generate lots and lots of traces and visualize them to sort of get a sense of the assumptions that are encoded in our model. So these are the sorts of data sets that our model is going to be able to explain. Right? But of course, what we really want to do is not just generate a bunch of fake data. We want to analyze real data and do inference about it. So what kinds of inference algorithms exist to do that? One of the simplest ones is called importance sampling. And the idea is that we're going to start with a data set. I'm using an especially simple data set because this algorithm you'll see is not going to be very strong, and I wanted to show success. Here's a really simple data set, and the algorithm proceeds by proposing an explanation for this data from a proposal distribution. So here I just proposed an explanation for the data. It's not a very good explanation. Right? It wasn't actually based on the data at all. I just had some distribution called a proposal distribution from which I sampled an explanation, which in this case was a curve, a noise thing, an outlier classification, right? But it's not related to the data at all. So it's not clear how this is going to be useful to us. But we can save it and do it again and do it again. And we can do this many, many times and get tons of potential proposed explanations for the data. And then we can weight them all according to an importance weighting formula that's going to weight up those samples that explain the data well, and that also are sort of, it's going to weight down samples that seem maybe overrepresented by the proposal distribution. So if our proposal is concentrating in one area, samples from that area are also going to be weighted down. Okay? And we can then use these weighted samples to do things like compute posterior expectations. We can take weighted averages across all of these samples. So you can see that a downside of this importance sampling algorithm is that you're just guessing blindly. And on a harder problem, you wind up doing very poorly. It's hard to see here, but if we do the importance weighting step, you'll see that even sort of our best example here is really bad. And that's because our proposal distribution just doesn't sample quadratics very often, for example, in this case, or cubics, right? Our proposal distribution was sampling the degree from a geometric distribution. And so what programmable inference is going to allow us to do is write our own proposal distribution, right? So we get to write the guesser ourselves. And it doesn't matter what information we take into account here, as long as we follow some simple, as long as we satisfy the soundness properties, the inference will still be sound. We'll still be getting samples that are approximately distributed according to the posterior. So our custom proposal is just another probabilistic program. And it's going to sample using the same names as the original algorithm. But now we can do things like sample a degree that has higher concentration in the regions that we think the degree might be. Or we can do things that don't even depend on the data, that are just smart things to do in a guessing algorithm. For example, here, after sampling a curve, when we're trying to decide the outlier status of each point, we can, so this does depend on the data, but it's going to look at the data, and it's going to see how far is the data from the curve, and use that to determine what probability to assign to being an outlier or not being an outlier, right? So our guesses now from the proposal distribution, we can also represent them as traces. They're going to share a lot of the same addresses, a lot of the same names as the model, except without the data. And our proposals are going to be a little bit better now. So we're going to see a lot more higher degree polynomials and also a lot more red here, because what our new proposal distribution is doing is after it samples a curve, it's intelligently assigning the outlier classifications, right? And now when we do our sort of importance weighting, we actually have gotten a few relatively good explanations here. Okay? So what are the requirements that have to be satisfied when using this programmable inference feature? Well, one of them is absolute continuity, which is a fancy way of saying that if there's some event that occurs with some positive probability under the model, it better occur with some positive probability under the proposal too, right? So this is a pretty intuitive requirement, which is saying that, you know, if the distribution from which you're generating your guesses is missing out on a whole region of the answer space, then no matter how long you run your inference algorithm, you're never going to cover that region of the answer space. And so this can't possibly converge to the right answer, right? Another thing that we have to make sure is that the densities, the importance weight is computed by computing a density ratio, which means that the densities have to be correct. And not only do they have to be correct individually, the densities of these probabilistic programs have to be computed according to the same base measure so that we can divide them and have it actually mean something. And probabilistic programming languages like Pyro and Gen have procedures for computing densities, but there are ways of writing programs that make those procedures behave in strange ways. So we need to ensure that that's not happening. So some things that could make importance sampling go wrong here are, you know, if the proposal assigns 0 probability to some degrees of polynomial, that's not good because it violates absolute continuity, right? Okay, I'm going to go a little bit quicker through the other inference algorithms just to give you a taste for them. MCMC is an iterative algorithm. So you can see it sort of doing a random walk here. It's basically doing a random walk through the space of explanations using a transition kernel, which takes you from one step to the next step probabilistically. And this is the Metropolis-Hastings algorithm. So after each step, it's proposing a possible next step and then accepting or rejecting it. And the probability of accepting or rejecting a step is calibrated to ensure that the stationary distribution of this Markov chain, so if we run it for a long enough time, it will converge to the posterior distribution. Okay? But you can see that it's not doing a great job, right? And that's because we're using the default transition kernel in a lot of probabilistic programming languages, which is not very good. We can achieve much better results if we write a custom transition kernel. And this one isn't even doing anything that smart. It's just blocking some of the variables together. So it's proposing not just one variable change at a time. It's proposing multiple variables changing at a time and adding some Gaussian drift moves to make sure that we can sort of fine-tune a good answer once we have it. Okay? But that freedom to write your own proposal distribution leads to just much better behavior. But again, it also is a double-edged sword that comes with new requirements. So for example, we have to make sure that if we write a custom transition proposal, it's reversible, which means that if it has some probability of taking us from region A to region B, it better have a way of taking us back from region B to region A again. Okay? And there are some other properties here too that I'm not going to go into detail in the talk, but please look at the paper. Variational inference we just heard a lot about, so I'm not going to spend a ton of time on it, but it is trying to optimize a guide or variational family to match our posterior distribution. And it's going to be sort of sampling from our guide. The training procedure is to sample from our guide, basically compute these importance weights, but there's a log in front So we're going to weight them. And then we're going to do a gradient update where we encourage the variational family to be better, put more probability on the samples that did well and less probability on the samples that did poorly. That's sort of what the score function estimator does. It's kind of reinforcement learning like, and it's the same objective that shows up in certain reinforcement learning algorithms. Okay? And again, we have some requirements that come with this, and we saw them in the last talk. Unlike the other algorithms in this talk, we don't handle variational inference fully. So the last talk was talking about a lot of requirements having to do with differentiability that we're not handling here. So these are some preconditions to variational inference being sound. The other algorithms we're actually going to prove sound in some sense. The variational inference ones, all that we're going to do with our system is prove that we satisfy certain preconditions. Okay. So there are all of these web of requirements for users of probabilistic programming systems with programmable inference. How do we actually make this manageable for the user? And so our solution is with types. So our basic approach is this. We have a graded monad for probabilistic programs. So a probabilistic program is going to be given the type p tau alpha, where alpha is a type parameter representing the return value. Sorry. Oh, OK. Sorry. I thought. So I'll just conclude by, sorry, I miscalculated the time here. The tau parameter there is going to track the space of possible execution traces. And we have sort of rules for return and bind in this language. And when you bind, you basically combine the traces of the two pieces of the monad. We have various sort of control flow features that are going to introduce sum types and lists into the trace, because your trace can basically contain lots of copies of something, or it contain either this or that when you branch. And this is going to allow us to create sound by construction versions of algorithms like importance sampling and Metropolis Hastings and so on. And we have a Haskell prototype, and the Haskell code looks a lot like the code in those figures. So thank you.
OK, thank you. Are there questions from the audience in the room?
So another problem of importance sampling is the variance can be infinite.
Yep.
Do you think about some way to check the finite variance?
Yeah, that's a great question. So there are a lot of properties that we might want to check of these inference algorithms that have to do with their quality. The property that we proved is, that you get you get properly weighted samples, but absolutely you can get variance that's unbounded if your proposal is too much sort of narrower than your target posterior distribution. So I don't have a great answer for how to check that. Some work that my colleague Marco presented yesterday is about sort of dynamic analyses that try to answer that question. So how can you actually, by running your inference algorithm a bunch of times and sort of doing inference about what the inference algorithm is doing, come up with bounds on the divergence between your inference algorithm and a gold standard inference algorithm that you have. So I think those kind of dynamic approaches are interesting to explore. I think it would be really interesting to see static approaches, but I'm not sure how to go about it. Yeah.
Other questions from the audience?
You're using types. Are you relying on the type system that's in your host language already, or do you have a new type checker? And if so, what?
Yeah, great. The reason that we implemented a Haskell prototype was to check, can GHC actually just infer these types for us? And the answer was yes, if we put enough extensions in. So we're using the row types package to sort of handle these record types that sort of grow as you build your monad. And GHC does a pretty good job of inferring everything. So the Haskell code on GitHub actually has all of the type annotations commented out so that you can verify that GHC is actually inferring those types for itself.
OK. If there are no more questions, let's thank the speaker again and move on to the last talk.